Today's advanced functions lesson is on solving inequations. So here's some notation. You've probably done work with union and intersection of sets in elementary school with Venn diagrams. So here's what union means. You've got two sets, A and B, and when we put them together, the union of them is the collection of all. So this is the way we write the notation. It's a U symbol, A union with B, X such that, sometimes this piece isn't here, X is an element of A or X is an element of B. And normally we just write it like this instead. A union cannot have duplicate elements. So if this group up here, A, is 1, 2, 3, and this group here is 2, 3, 4, then when we put them together, we would have 1 on the A side and then 2, 3 because they overlap, and then 4 over here. So we wouldn't write 2 and 3 twice. Example 1. Solve the following factorable polynomial inequality algebraically. So this is new, having this inequality sign here. The question tells us it's factorable, so that's going to help. Step 1 is going to move all terms to one side. Remember we talked about which side to move it to. We usually want the leading coefficient to be positive. In this case, that would be the cubic. The leading coefficient on the cubic, I want that to be positive. I don't have to, but it does make calculations a little easier. So I'm moving everything to the left, and now I have less than or equal to 0. I'm going to call that f at x, and I'm going to forget about the inequality for now. I'm just going to look at the polynomial that I have here, my new cubic. I'm going to factor my new or my related or my corresponding function. So this new one that I've called f at x, I'm going to factor that. To do that, the first thing we're going to do is a factor theorem. We know we can use a factor theorem because it says it's factorable. So I'm going to have to find something will factor. There are possible zeros, plus or minus p over q, so factor theorem. We're going to list them here. So the possible zeros, so 6 is our constant. So anything that's a factor of 6 over anything that's a factor of 2 and all of those combinations. So we've got plus or minus 6 over 2, and we've got plus or minus 6 over 1. Then we have plus or minus 3 over 2 and plus or minus 3 over 1. What else do I need? Am I missing anything? Yes, I'm missing plus or minus, let's put them over here, plus or minus 2 over 2 and plus or minus 2 over 1. Now I've got some repetition happening here, but we'll talk about that in a second. And I've got plus or minus, I'll put it over here beside the 3, plus or minus 1 over 2 and plus or minus 1 over 1. So here's some repetition I have. Let me just change to purple here. 6 over 2, that's the same as 3. So I've got plus or minus 3. That's here again, right? So I'm not going to rewrite that one. Then I've got plus or minus 6 over 1 is the same as plus or minus 6. Plus or minus 3 over 2. Plus or minus 1 over 2. Now 1 over 1 is the same as 2 over 2. So I'm just going to write that once as plus or minus 1. And then here is plus or minus 2. So that's a lot of different options here. We go through them and we find one. Always start with the 1, the plus 1, the minus 1, the plus 2, the minus 2. Usually you're going to find one pretty quickly there. So sub in to your related or your corresponding function. We're going to sub these values in here until we find 0. So go ahead and do that and come back when you've found one. So f at negative 2 is equal to 0. So that means x plus 2 is a factor. What's the next step after we find a factor? So we use the factor theorem. Now we're going to divide. You can use synthetic division or long division. And I can hear all of you. I know you're saying synthetic because it is faster and quicker. I prefer long division, but we'll do synthetic because this is going to be a crowded page. So let's do synthetic division here. Remember what the number that we subbed in that worked, that factor goes here. And then our coefficients and our constant from our function go into these spots here. We bring down the 2. We multiply the -2 times +2. That gives us a -4. And then we add these two pieces here. That gives us a -5. Do it all again. -2 times -5 is 10. -13 and 10 is -3. And the last step, -2 times -3 is 6. And we have here our remainder is 0. So let's put all of that together. That gives us, here's our original one that we found with our factor theorem. There's our x plus 2 in red. It's this red piece here. Then this comes from these coefficients here in the constant. This is a trinomial, a quadratic, which we can factor. So we have this all factored now. And we can say, therefore, x is equal to 2, -1/2, and 3. If we were back in chapter 3 or even earlier in chapter 4, we would be done now. But of course, we want to make it more exciting than this. This isn't really what the question was asking. The question didn't say when is x equal to, right? It's not solving. This was an inequality up here. So now is where we have to add on some more steps. So everything we've done up to now is review really all these steps, but we're not finished because this is an inequality. So what we're going to do, there's a couple of ways to solve it now. We can create a chart or we could graph the corresponding function. Remember, the corresponding function is this one here or this one here. I'm going to do the more complicated method right now, which is to do a chart. Now you don't have to do the chart. It does take longer, but we'll need to do it later in this unit, in this course. So we're going to be introduced to it right now. So here's what the chart looks like. What you do with the chart is you have to figure out how many columns and rows you need here. And the way you do that is you take a look at your factored equation here. So I'm going to take these zeros and putting them in order low to high, I would have, well, they are in order, so we can leave them like that. So you want to make sure these are in order, low to high. And then since we're looking for an inequality, I'm going to go to the top row, the interval row here. And across from the word interval, I'm going to use all of those numbers and use them to go from -∞ to +∞. So what that means is we're going to look for x values that are less than -2, not less than or equal to, I'll talk about that later, just less than -2. So I start with my first number. I want to look on the left side of -2. Then I need to look in between these two numbers to see if my solution is in between these two numbers. So I'm going from -2 to x to -1/2. That's my next interval. My next interval will be between -1/2 and 3. So in between those two, -1/2 and 3. So think of a number line. If I had a number line up here, here's 0, -1, -2. So I'm trying to look at all possibilities. 3, so 2. So I'm trying to look at all possibilities of all real numbers. So -2 is here. I've got to look on this side of -2. I've got to look between, here's my -1/2. I've got to look between these values here. So I'm really taking into account every possible number of the real numbers, of the real number set based on the zeros that we found. So I still need to look at all x values greater than 3. So that's a complicated part there, but once you understand how to set up the intervals, the rest of it's going to fall into place really easily. Below that, below the word interval on the chart, you'll see test value. So we've now covered, we're going to look at every real number on the number line system. We're going to look at them all. So the next thing you have to talk about is a test value. So what I'm going to put below the test, I'll use beside here. Beside the test value, I'm looking for a number, pick a number that's less than -2. So the easiest one would be -3, but you could pick -200 if you wanted to. So -3 is a number that's less than -2. Now what's a number that is in between -2 and -1/2? We want to make life easy on ourselves. Let's pick -1. We're going to sub these numbers in, so we're looking for numbers that we can sub in later that aren't going to be too challenging. Anytime you have one end that's a negative and one end that's a positive like this, you want to pick 0. That's really easy to sub in. Pick a number that's greater than 3, pick 4 or 5 or 6, doesn't matter. Those are our test values. Okay, the next part we're going to do, underneath the word test value, all of our factors go in here. So I'm going to write all of the factors, if I can fit this in here. Factors go along here, that's an F. Factors go in here. So we factored it. It doesn't matter what order you put your factors in. X plus 2, 2x plus 1, and x minus 3. Now, if I'd also had a greatest common factor at the beginning and I'd pulled out like a -5, that would go in this list too. But I don't have a greatest common factor. So that goes in the factor spot. Now what I'm going to do is look at those test values and sub in. So this is how I knew how big to make my chart. I knew, well, I did the chart in advance, but I knew I wanted to have the word interval, the word test value, and then my factors here, and then I need a spot for my answer later. And across the top, I need as many intervals as I could get from my zeros. So my test value is x minus 3. So I'm going to take -3, sorry. I'm going to take -3 and I'm going to sub it into each of these brackets. So it's the same as taking -3, putting it in here, put -3, -3, -3, but I don't care what the number is. When I sub a -3 in here, -3 plus 2 is going to give me a -1. I don't need to worry about the number, I only need to worry about the sign, because we're talking about inequalities here. We're looking for positives and negatives when something is greater than the other or less than the other. So in this box below the -3, when I sub a -3 in to x plus 2, it's a negative. Now when I sub a -3 into 2x plus 1, that will also give me a negative. I'm just going to put a negative sign there. And sub -3 into x minus 3, and I get another negative. So I'm getting a negative here and here. So what I'm kind of determining now is what's happening on this. Look at the number line up here on the right. I'm kind of figuring out what's happening here with the -3. What's happening with all those? It's going to be whether I picked a -3 or a -200, I would get the same answer on that end of the number line. Let's look at the -1. We sub a -1 into our first factor, which is x plus 2, and we get a positive. We sub a -1 into our second factor, it will be a negative, and as will our last one be a negative. 0 is easy to sub in. 0 to x plus 2, that will be a positive. Into 2x plus 1, 2x plus 1, sub in a 0 there, we're going to get a positive. And sub in a 0 there, we get a negative. The last part of our number line, the last part of our numbers that we're going to look at are the numbers that are bigger than 3. So we subbed in, we picked a 4, could have picked a million if we wanted to. Sub them into each of the factors here and write down the sign of what you get when you sub in a 4. All of these are positive. So now our very last section here that I'm going to put in, the reason we're calculating all this is what we're actually looking for is we're looking for what the sign of the entire function is. So I'm looking for the sign of f at x. That's what my last row is all about here. So let me go back up to the factored form right here. If I had subbed a -3 in here, I'd get a negative in one factor, a negative in another factor, a negative in another factor, negative, negative, negative. That means the whole function, 3 negatives, I don't care about the number, negative times a negative times a negative is a negative. That means the sign of f at x when x is less than 2 is a negative. 3 negatives make a negative. The next column, we have a negative, 2 negatives and a positive. That will give us a positive. So we're taking these 3 and we're seeing what they simplify. So a positive and a positive, these two make a positive and a negative together make a negative. And last column, 3 positives make a positive. So we have our finished column here. we now know the sign of f at x. We know when it's positive and when it's negative. So what, right? Why did we do all that? Remember what we were looking for originally? Well, originally was when this cubic is less than this quadratic, or when we put it all together, when this new cubic is less than or equal to 0. So this chart tells us when our function is less than or equal to 0, because when our function is less than or equal to 0, it's negative. So now we can come up with our solution statement, and we're going to use our new union symbol here. Before I do that, a little explanation. Since our inequation was 2x cubed minus x squared minus 13x minus 6 less than, that's this one here. That means our factored version is, so here's our factored version, and we're making it less than or equal to 0, meaning we're looking for where the graph is below the x-axis. The final answer will be the intervals that are negative. So this is one of our answers because we got a negative, and this column here is our other answer. And that's set notation, not perfect set notation, but this gives us our answer to this question. So let me put it in proper set notation here. I'll put it down below. So proper set notation is, this is what we did in, grade 11. X is an element of real numbers such that we have this piece here that comes from, in the chart, that comes from the first answer because we had a negative. Remember, we're looking for where our function is less than or equal to 0. So it's less than or equal to 0. Now is when I put in my x is less than or equal to negative 2. Because the question had a less than or equal to, the equal part, I have to include it here. I didn't include it up in my intervals only because, so in my intervals I just used less than. I didn't use less than or equal to, even though that was the original question. I just used less than because I don't want to think that I can sub in a negative 2 here. If I wrote less than or equal to negative 2, then I might sub in a negative 2, and then I'd get a 0 here, and I don't want to do that. So usually you can put the full symbol in here, but I tend to just put the less than or the greater than because I don't want to accidentally sub in a number. Not that I would, but you might. Okay, so x is less than or equal to negative 2, union with this piece, negative 1/2, less than or equal to x, less than or equal to 3. So that's set notation, that's the answer in set notation. I'm going to show you the answer in interval notation as well. So interval notation, I'll change colors. Interval notation looks like this. We just start with x, so interval notation is faster to write. X is an element of, now I don't put real numbers, I'm just putting x as an element of. The way I write this in interval notation, so x is less than negative 2, that's saying from negative infinity all the way to negative 2, including negative 2, so it gets a square bracket. And then the union symbol. The second piece, so because of these, I have square brackets, not round brackets. Negative 1/2, comma, 3, square bracket. So that's interval notation there. It's a little faster to write. It's like you're writing coordinates, but what your coordinates, the values that you're putting in the brackets are actually the endpoints, the very far left and the very far right. In this case, negative is infinity is the very far left, and the very far right is negative 2. Last thing we're going to do is verify with graphing technology. So here was the original question we had. We had a cubic less than or equal to a quadratic. So here's with the cubic there, I matched them with the colors. So the cubic is green, and when is it less than or equal to the quadratic? So I use Desmos. I see the points of intersection are these dark black dots here. And in set notation, this is the answer. So the green one is less than the purple one when our x values are less than or equal to negative 2. And the green one is lower here in this little piece that I'm highlighting here. That's from an x value of negative 5 until an x value of 3. So that's when the green one is less than the purple one. But what we did was we took those two equations and we put them together into a new corresponding equation. So let's look at that new cubic. Here's the new cubic. It looks different than the other cubic or the quadratic, but look at where it's much easier to find where this function is less than or equal to 0, right? I just look along the x-axis. It's less than or equal to 0. I look at the zeros. We found those zeros pretty easily with our factor theorem and with synthetic division. Then we're just looking for where the function is less than 0. So this would have been pretty easy to graph on our own. So remember at the beginning I said I'm going to show you the more complicated method, which is the chart method. Once we factor this, I'm going to rewrite the factors here. So once I got these factors, I didn't really have to go and do all the work that I did because it would be faster for me to use my knowledge of graphing. I know that the leading coefficient is positive, right there, it's a 2. I know it's a cubic, so I know the cubic has this shape, right? It's starting down here, it's going up. I also know I have a straight through 0 at -2. I have a straight through or linear shape 0 at -1/2 and at 3. So I could have drawn this graph really easily and then looked at it and said, okay, where is this graph less than or equal to 0? It's less than or equal to 0. Let me put the highlighter on here. It's less than or equal to 0 here. Whoops. This part is less than or equal to 0, and this part is less than or equal to 0. So that's a much faster way to do it, and for sure you can do that in your homework. You are going to have to use the chart later, so that's why I'm introducing it to you here. But if you're doing a bunch of questions in your homework, do a quick sketch, use all the skills. You have tons of skills for graphing these, and then you're going to come up with your answer just by using your graph. So you don't need to do all the work, but I do recommend you do the chart a few times today so that you get comfortable with it. Let's do a word problem. The portion of a path of a meandering river, this is a meandering river, it was mapped by university geography students and modeled by this function, where r is the river's position in meters with respect to x, which was mapped on their grid. So they have a grid, they have put this on a grid, maybe their y-axis is here, and their x-axis is here, and this is the function. Sketch a possible graph to determine the river's when the river's path is 11 meters above the horizontal surface. So if we're going to set up a new inequality, so you got to think about this when it says when the path is at least 11 meters, at least 11 meters. So this function, when is it at least 11 meters? So does at least mean greater than or less than or greater than or equal to or less than or equal to? So think about it if I said you have to be at least 16 to take this course. Does that mean you can be 16 or you have to be 17? So at least means greater than or equal to. So we're looking for where this function is greater than or equal to 11. So I just substituted in the function there that was given in the question. But this one is already factored, so a lot of work has been done. What I'm going to do this time is I'm going to graph just r at x. I'm going to forget about the 11 because if I were to expand all of this, bring the 11 over, try to factor it again, it might be unfactorable, but even still, it's going to take me a really long time. The question doesn't tell me I have to factor it. It just says sketch a possible graph. So I'm going to sketch a graph without doing all of the algebra because it's already factored for me. So how do we graph it? Well, we look at the information we get from our factored form of the function here. We know the degree is 4 because this one has this double root, it has 2 x's, this has 1, this has 1, that's a degree of 4. The leading coefficient is going to be positive. Again, if I multiplied so there's an x, I would have another x there, I would have a 3x, and I'd multiply that with this x, I would have a positive leading coefficient. The zeros, so I've got a bounce here because of this power of 2. The order is 2. That means that's a bounce 0, so it's going to open up or open down. This one, the middle one, is going to give me a, oops, I'm on the wrong pen. The middle one is going to give me a straight through 0 right here. This is going to give me, it orders 1, so it's going to be a straight through 0, and it's going to be at x equals -1/3. And then the last one, that's the easy one, that's x equals -5, and that will be a straight through 0. This one is x equals -2, but it's a bounce. So that one's kind of special. What else do we know by looking at that? Just the factored part, not the 11. We know the y-intercept is at 0 and 20. So what do we do next? We're going to graph it. That's what the question asked us to do. So you think about where your x-axis and your y-axis need to be. Because of the -5 then in my zeros, I need a little bit more space on the left side. So I put my y-axis there. You don't have to. You can go right through the middle. There's my x-axis. So next thing I want to do is put on, I want to graph it. So let's put on a scale on our x-axis and our y-axis. Remember, we've got to get a y-intercept of 20 on there. So we want to make sure that fits. So I chose a y-axis scale of 5s so that I could make sure that my 20 gets on there. And my x-axis scale, I'm going to actually spread it out because I don't have a lot of, all my x values are negative, and the biggest one's a -5. I have lots of space. I'll probably I'm going to count by 0.5s for my x-axis. So let's start by placing our zeros. We've got one at -5, -1/3. That's kind of hard to do. I'll put that about there. And then I have another x-intercept at -2, and that's my bounce. So how do I know if it's bouncing up or bouncing down? What other information have I got? The degree is 4. So that means this could have a W shape or an M shape. It's not going to be the flattened parabola because I have 3 zeros here, so it's going to have the W or the M shape. My leading coefficient is positive. So my leading coefficient is positive. That means it's got the W shape, not the M shape. I've got the zeros on there. The y-intercept is 20. Let's put that on. That's going to help me to get a better idea of the shape here. So I know I have a W shape, so it's going to come down here. -5 is my first zero, and now I know about my bounce. It's going to bounce like that, come back, turn around. Maybe it's going to go way down, I don't know. And it's going to come back up here and through my y-intercept. So let's try and draw that. Actually, before we draw that, let's do one more thing. We're going to talk about test values. Well, we'll do, okay, let's go ahead. We'll draw it and then we'll do this next thing. So we'll go ahead and draw the shape, and then I'll tell you when the 11 comes into place, because we haven't really talked about the 11 yet. Test values, by that I mean, we've talked about this before. In between the zeros, you can pick a point, like say -3, sub in a -3 just into this side, get an answer, and then you'll kind of make sure that you should be below the x-axis, right? When you sub in a -3, you shouldn't be above here because we already talked about what the shape of the graph is. So you can use some test values here. You can pick a few other points just to make sure. You can pick -6 and make sure you're in the right spot. So test values, they take a few seconds to calculate a few, but they just help confirm you're drawing it the right way. Okay, I got kind of wobbly in there, but that's a possible graph. That's what we have to do, a possible graph. So we've graphed this piece here using this information, and maybe you used some test points just to make sure that it was looking good, got a few values in there. But now we have to actually find out where the function is greater than or equal to 11. So for this one, I'm going to have to go to 11 on my y-axis, draw a straight line across, and then see where it hits my green curve. So here's my line y equals 11, and I'm looking for where my function is greater than or equal to, remember it said at least 11 meters. So I have to include the point of intersection. So wherever it looks like on your graph you're intersecting, and then above it. So in my answer, according to my graph, I would say the first point of intersection is about, let me put it in black here. This looks like here we have an x value of approximately, let's say, -5.2. The other point of intersection I'm going to say is approximately x equals -0.4, -0.3 maybe. So those are my approximate points of intersection. So that means our function, r at x, is greater than or equal to 11 when we have, so let's do set notation, x is an element of real numbers such that when we have any x values that are less than or equal to negative 5.2. And the reason I'm saying less than or equal to is because we're looking for where we're above our line y equals 11, at least. So this is when our graph is at least 11. So all of this section here, and then all of this section here. So I'll use my union symbol and union with all of the x values that are greater than or equal to negative 0.3. So that's the set notation. And this is just, we already talked about test values where you can sub them in to check. So you could sub in some more values if you wanted to check here. And then concluding statement in set notation, I've already done that. So because it's a word problem, I also need a sentence, a regular sentence. So I need a therefore sentence. And we're talking about the path of the river. So therefore, the path of the river, is at least 11 meters above the horizontal axis when, and the last part I will use, I'm not going to write in words, I'm just going to use my notation, when x is less than negative 5.2 or when x is greater than or equal to negative 0.3. Let me fix my x there. So there's our answer for example 2 when we're just graphing. Example 3. At the start of a log flume ride in an amusement park, this is a log flume ride, an electric motor raises the log to the top of a hill. There's the top. Then the log descends under the influence of gravity. The log speeds up enough to carry it over the rest of the hills. As the log descends the lift hill, so this is the lift hill here, this is the function that models its height in meters. So notice we have a restricted d distance. So d is a horizontal distance just between 0 and 100 meters. It's not for the entire path of the ride, it's just for these first 100 meters. It's quadratic, right? And the leading coefficient is positive. So that would be a quadratic that opens up. Now obviously this ride isn't going to continue to go up to infinity, so we have a restricted domain. As the log nears its lowest point, that would be its vertex, if the vertex falls in here, it passes through water. The surface of the water is about 2.5 meters above the ground. Use graphing technology to determine which intervals the riders will get wet. That's awesome. That means we get to use Desmos. And you don't have to, you could complete the square and find the vertex. You could use a quadratic formula to find the zeros. It's quadratic. There's a lot you could do with it. But the question just says use graphing technology. So I put this into Desmos, and then I had to play around a bit with my scale because it was compressed, but I got it to look like this. So here's the equation. And then I want to know, this is an important part here, when the water 2.5 meters above the ground. So I had to put in the equation y equals 2.5. There's that blue line there using Desmos. So using graphing technology, when will the riders get wet? So I just look at my graph here. If you're in Desmos, if you just click, there'll be little gray dots already showing up. So I just click on those dots themselves and it darkens them and it puts the coordinates right in. So using those values, I can see the riders will get wet at approximately 52.9 meters until 67.1, should be meters there, horizontal distance. So this is not time, this axis is not time. It tells you in the question that D is the horizontal distance. So this is the horizontal distance that they're traveling. So once they hit about 52, 53 meters, they start getting wet, they go down, and then they're back up again. So that's the end of that question. And that's the end of today's lesson on inequations.